All right, students, welcome to Chapter 9, Data Design. Now, in Part 1 here, we're going to talk about databases versus the old traditional flat files or file-based systems versus database management systems. And then also we're going to look at entity relationship diagrams. So let's jump in. Here are the objectives. I would encourage you to pause and review these. We're going to talk about some of these in Part 1 and then the rest in Part 2. So let's jump into this. First of all, we've talked a lot already about data structures, and the idea of formatting data so that it's usable, so that it's non-redundant within a system, so that it holds as much purpose as it can, giving back as much information, because again, there is a cost with data. It's whatever cost is associated with us getting the data into the system, storing the data, securing the data, backing up the data, all of which we do so that we can query the data to get valuable information to help us run our businesses and other aspects. So each file contains data about people, places, things, events, you name it. We've talked about the difference between an enterprise resource system, a single system that does everything a business needs versus a business that runs off of multiple systems. So the example given here, Mario and Danica. So in Mario's auto shop, he relies on two file-oriented systems that store data in separate files that are not connected. Now, what that means is if you think about it, and we'll see this here in a minute, Mario's system most likely has data that is the same and needs to be kept and maintained the same in two different systems because they don't link into one system, whereas Danica uses a database management system with multiple tables that join data together. So she has the opportunity here of storing data only one time in a single system versus needing to store the same data in multiple systems. So here's an example on the left, if you notice. So he has a mechanic system and a job system, mechanic number, name, pay rate, etc., insurance. That mechanic's going to work on jobs. So you can see that there's a natural linkage that would want to link those two systems together. And the cost effectiveness of this, not very effective in the fact that if we do want to transfer data, we then have to build a third piece or a third system called middleware that would transfer the data back and forth. Whereas you can see in Danica's system here, she has a single system. The system is comprised of tables, each table storing specific information. So as you can see, we have a mechanic table that's going to list the mechanic and the mechanic's information. And we're going to be able to use like a mechanic ID to link it to an individual job record that the mechanic or mechanics may work on. So some people ask, is file processing still important? Yes, it is. Batch processing is done. The college does it, for example, whereas information from systems outside of the main banner system at our college generates data, generates a file. Those are batch processed, every so often, every few hours during the day. Why? Because there's huge transactions. We're getting ready to get into that time where you're registering for classes for fall or for next term. And think of all the transactions that are created when you go in and register for 2 to 3 classes, and we have thousands of students doing that. So, great example there. Database environment, is a database management system is a collection of tools, features, and interfaces that enables users to add, update, manage, access, and analyze data. So we've seen these systems grow. It used to be just the database. Now we can get a subset of reporting tools and querying tools and other things within this system. We might even get some standard interfaces or PKIs environments where we have some standardized ways of pulling and sending data to the database so that we can use different interfaces basically to get the data in. It may be web-based, it may be client-based, you name it. So design concepts, we'll talk a little bit about this. So here we see transactions, and then a customer record. So, we take the transaction, we add them together, we put them over in the customer record, and that gives us a balance like for a month or for a series of transactions. So database management systems, great thing about them, first of all, standardized tools. So a lot of times, just because we're working in, say, Microsoft SQL Server, we understand a lot of the concepts that may be in MySQL, an open source database system, that might be an Oracle system. So when we play together, yes, they might be implemented differently, the language might be different, but we understand the standards for database management systems and managing those databases. So database management systems are definitely highly scalable. If you think about it, I'm sure you realize that websites like Facebook are managed on hundreds, if not thousands, of databases that store specific information, bring it all together so that you can have your Facebook experience, whether you're playing games, communicating with friends, posting pictures, you name it. Database design allows better utilization of hardware. It certainly does. From the aspect of, again, scalability, optimizing the hardware, enterprise-wide, so accesses requirements and maintains the data, for the entire organization. So again, ultimately, we would like to have one company with a single database. That's what we get with an ERP system. That way, we're not having multiple systems that have the same information, all systems needing to be updated. It just doesn't work as efficiently. With a database management system, we do have better security. We can create encrypted tables that store just the data we need encrypted. So again, from an efficiency standpoint, we're not having to encrypt our entire customer table. We might have some payment information offset from the customer record where we store what their current credit card is, etc. But we link it, say, with the customer number, so that we just have to encrypt the data that needs encrypting. So that creates a lot of efficiency for the system. Not all of the information needs to be de-encrypted or encrypted each time we make a transaction. So design provides a DBA flexibility to alter data structures without modifying information systems that use the data. So again, we're just talking about the core data and storing the core data. How we use the data, how we get the data into the system can literally be independent. So I love this graphic here. We have the database administrator who manages and manipulates the data. They do it with the schema, sub-schemas, with SQL language, etc. And then if you notice down at the bottom are the people that utilize the data or put the data into the system, as well as the related information systems that may be pulling or pushing data into the database. So again, this doesn't have to be one single interface or one single source of data. This can be many sources of data that are bringing the information in and storing it in specific tables or a related series of tables based on the data that's being brought in. So, users typically work with predefined queries and switchboard commands. Those are things that they're not programming the database. They're just utilizing tools that have been given to them, maybe by the database administrator, maybe by database programmers. So administrators are concerned with the access, providing quality data, storing quality data, backing up, of course, and recovering data, being able to secure it, audit it, see who brought the data in, who manipulated the data, who changed the data, and then, of course, supporting users' needs. A lot of times, database administrators also know how to create database reports. So related information systems can support several related information systems that provide input into the required system. So again, we can get input or output even out to a website, out to an email, out to a text message, out to a client application that interfaces, out to a third party or a third series of secure servers, for example. And I'll give you an example of that in a little bit. So a database manipulation language is what we use, just like a programming language. Nothing real interesting about it. It's just specific to a database. It includes how we're going to operate the database, store information, retrieve, update, delete data as it comes in from those sources. So a schema, as we've talked about, a schema is the attributes of the database. So we've talked about objects already. We've talked about methods and attributes. The schema is that for a database. So it includes information on the fields and the tables and the relationships between them, and the cardinality between them. That's all encompassed in the schema. And then, of course, the physical data repository itself is the complete definition of the database. So if you think about this, we've done a data dictionary. That's where we're going to start creating this database, folks. From that data dictionary, we're going to figure out what the relationships are between the data elements, what tables they need to be stored in, what attributes each table has. That's a field. How many records or what might be stored in a record. So an example would be a customer table that has all the information about each and every one of our customers, for example. So that's also stored in the database. So one of the, focused areas, I guess you would say, of databases today is connecting to the web. So the example I'd like to give you here is WordPress or Joomla. You might be familiar with those tools for designing websites and web services, and started out with blogs, yes, but they've grown, extensively. A WordPress site works with a database on the back end. So in this case, for a lot of us, it's already pre-programmed, and we're just doing the site-specific information, all of which is stored in a database. The pictures, the blogs, the way the menu is structured, the navigation, all stored in a database and uses HTML. Now, we're starting to see other technologies such as XML, extensible markup language, being used for data transfer requests and commands, into a database from the data standpoint. So from the metadata sort of standpoint there. And then, of course, security. So when we talk about security, one of the great things is we don't necessarily have to open the entire database up to the web. We can actually have what's called a front-end server. I'll give you an example of this. In Microsoft Exchange runs with a database, and Exchange is an email server that stores emails. So the idea here then is that we can transfer or have a copy of our master database that transfers the information back and forth to a sub-database called a front-end database that has just the information that's needed, maybe just for the session for the client that's accessing their email. And then we can turn that back off and secure the data. That way, we're not opening up the entire database. We're opening up just the data that's needed to be processed through the web. Excuse me. So web-based, it is global access for sure. We try to design with some standards, interfacing with a standard browser, for example. It is ease of use. It's a familiar interface. As we create buttons and commands and stuff, we're using those things that users are used to seeing within their browser. So it works really well in that aspect. So multiple platforms, yes, because again, the database may be specific, but we can go ahead and provide the data across Mac, Unix, Linux, etc. by using, again, a standardized web browser, for example. Hugely cost effective because, again, from a programming standpoint, we're not having to program for Mac and PC and Unix and the Android operating system and this. We're programming an interface that works across all of those base platforms. Is there security issues? Yes, it is a universal issue, especially as we push more data to the web. Security is definitely an issue because as we allow data to be accessed, updated, manipulated from the web, that also means that a hacker could potentially have the same access as well. So, we need to take much more focus as we bring information or data outside of the secure walls of our company and bring it out to the web, now suddenly potentially people have access to it that shouldn't. So we need to have better passwords. We need to have better password policies. We need to make sure that the security mechanisms we're using, whether that be a secure socket layer, HTTPS, for those folks that don't know what an SSL is, that be up to date, that be secure. And also, a lot of times for security, it is proactive monitoring to see where from the internet our data is being accessed. So here's a quick, example when a client workstation requests a web page. Now, notice here, just because we're inside our organization doesn't mean we can't use web-based technologies to create intranets. You all are familiar with the internet, but intranets, an example of an intranet-based application would be SharePoint. SharePoint is a web-based application, works on a database backend, SQL Server, of course, because it's Microsoft. But we can utilize these tools to create very highly productive environments inside of our organization. So again, all web-based. And what that means is as our users go from inside our organization to working from home to working while traveling, as long as they have secure access into our network, they can get that data and be productive literally anywhere, anytime within the world. So design terms. So when we talk about an entity, it's a person, place, or thing, or event for which data is collected. So example of that, a customer. A customer is an entity. We have data that we're going to collect on a customer. Okay. A table or a file contains a set of related records that store data about a specific entity. So we would have a customer table, for example, okay, that stores information about each and every customer that we have. In that customer table are going to be fields. These are attributes for those of you that remember our object lecture. These are attributes that describe the record, the customer record, that describe the entity. So an example would be customer first name, customer last name, customer street number, customer street name. Notice I didn't just say customer address, because I might want to sort by the street name, so I need to keep that number separate. Customer email address, customer mobile phone, customer home phone. You get the idea. And then, of course, a record, like I said, okay, also called a tuple, that's funny, is a set of related fields that describes one instance. So a record is going to be a row. If we think about Excel, it's going to be a row within that table that describes a specific customer. So in order to do all this, we need to have a unique way of identifying each record within a table, and we do that by a primary key. So it used to be, believe it or not, when databases first started, folks would use things like social security numbers, oh my gosh, as the primary key, because it was automatically a unique number that each person had. However, today we know that that's not such a great idea. So what we use is a thing called a primary key, and that's a field or a combination of fields that uniquely and minimally identifies a particular member. So instantaneously in a database, when we create a new customer, we're going to give it the next customer number within our customer numbering sequence. So a candidate key is any field that could serve as a primary key is called a candidate key. So something that is unique about that record could potentially be a candidate key, okay? Or a combination, again, of things. So, but be careful, we might think to use, this is a poor example actually, but to use like a customer first name, customer last name. But if you think about those might not actually be unique if we have enough customers, right? So a foreign key, a common field that exists in more than one table and can be used to form a relationship or link between the tables. So an example might be we have a customer number and then we have an order table, and we use that customer number in the order table to identify what customer data is associated with that order. A secondary key is a field or combination that can be used to access or retrieve data. So Again, that might be a unique identifier that we put in there so that we know how to get data back out of our database. So not only do we need to have something that uniquely identifies the record, the information of the data, like a work order number. We're never going to have the same work order number twice in a system. But we also need to have information that refers or keeps accuracy, relationships between the data. Okay, so it is a set of rules that avoids data inconsistency and quality problems. So let me give you an example here. Referential integrity. In order to put in a customer order, we must have a customer. So does that make sense? So in order to put in a job, assign a job in this case, the mechanic number becomes the referential integrity. So in order to put in a job, the job needs to have a mechanic number. A mechanic number must be assigned to each job. So that brings us to entity relationship diagrams, and we've seen these already a little bit as we talked about objects. You know, ERDs, so 3 types of ERDs, one-to-one, one-to-many, and many-to-many. So those are the 3 types. So let's just quickly take a look at them. So in this case, we're given some examples of a one-to-one entity relationship. That is that one manager heads one office. One vehicle ID is assigned to only one vehicle. And there's our great example. One social security number is assigned to one person. So that's the relationship there. Then we move on to one-to-many. This is where one department can employ many employees. One individual can own many automobiles. One customer can place many orders. One faculty advisor can advise many students. And then to the many-to-many. So students can enroll in many classes. A student would enroll in just one class, right? A passenger can reserve seats, or passengers can reserve seats on many flights. So many-to-many. So basically many flights can have many passengers. Could go the same way. Many products could be on many orders. So here's an example of a more complex entity relationship diagram. We can see that one sales rep can serve many customers. One customer can place many orders. One order can list many orders, can list many products. And then, of course, you know, many products are stored in one. So there's that reverse order we talked about, warehouse. All right, so cardinality is the idea, and again, we've already talked about this. This is sort of redundant. Here's how we describe that using what I call crow's foot, or I call it chicken scratches. Okay, so we have one and only one, one-to-many, so the one-to-many, 0 or one-to-many, okay, and then 0-1. So this is how we would describe it. You know, it's a numeric relationship, again, between those two entities, you know, how instances of one entity relate to others. So we could go back and take our previous examples and use the crow's foot notation to graphically represent what we were talking about from the one-to-many. I happen to like just the use of the, you know, one-to-one, one-to-many, N-to-M examples there. So a little bit more information. So here are examples of using that crow foot. So customer, you know, many customers can place 0 to many orders. And then you could pause and go through the rest. All right, so let's go ahead and pause right there, and we'll finish in part 2.